We're not the first. I want you to sit with that sentence for a moment before I explain what I mean by it, because it's the kind of sentence that can mean many different things. It can be vague, it can be mystical, it can be the setup for a story that doesn't hold up scientifically. So let me be precise about exactly what I'm claiming and why I'm claiming it and what the evidence actually says. The claim is not that there was a civilization before ours, not that some ancient humanity existed in a previous cosmic era and left ruins that we might someday find. The claim is more fundamental and more extraordinary than that. The claim, supported by a specific body of theoretical work and observational data that I want to walk you through carefully, is that our universe was not the first universe. That before the Big Bang that gave rise to everything we can observe, there was something, not nothing, not a void, not an absence of physics, something. A prior state of the cosmos with its own physical processes, its own history, its own structures, a state from which our universe emerged. And the evidence, the specific, testable, observational evidence is written in the oldest light we can detect. In the cosmic microwave background radiation, the relic glow of the early universe, which has been mapped with extraordinary precision by satellites like Planck and WMAP, written there in the specific pattern of temperature fluctuations, in specific anomalies and features that standard inflationary cosmology either struggles to explain or doesn't predict at all, are hints, signals, marks left by the pre-Big Bang universe on the universe that came after. This is not fringe science. The specific theoretical framework I'm going to describe, conformal cyclic cosmology, or CCC, developed by Roger Penrose, is the work of one of the most distinguished mathematical physicists alive. The observational analysis, the search for specific predicted signals in the CMB, has been conducted by serious researchers, published in peer-reviewed journals, and is actively discussed and debated in the cosmological community. It hasn't been proven. I want to be completely clear about that. It is a hypothesis, a serious, mathematically grounded, observationally motivated hypothesis, but not a confirmed theory. The evidence is suggestive, not conclusive. The debate continues. But the idea itself that the CMB might contain echoes of a universe before ours is one of the most extraordinary ideas in modern theoretical cosmology. And the specific signatures being searched for and the specific anomalies that have been reported are genuinely interesting and genuinely in tension with the simplest models of inflation. So let's go there from the beginning. Let me start with what Roger Penrose found when he thought carefully about a question that most cosmologists treat as settled. What happens at the end of the universe? The standard picture, which we've discussed in earlier conversations, is the heat death in an accelerating universe dominated by dark energy. Galaxies gradually recede from each other, stars exhaust their nuclear fuel and die, black holes slowly evaporate through Hawking radiation over unimaginably long timescales, and eventually the universe reaches a state of maximum entropy. A cold, dark, nearly featureless expanse, a few isolated photons and neutrinos, nothing else, separated by vast distances in an ever-expanding void. This is the big freeze, the quiet end of things, not a dramatic catastrophe, but a slow, patient, almost peaceful death. Penrose looked at this picture and noticed something that I think is one of the most beautiful and subtle observations in modern cosmology. He noticed that the end state of the universe, the heat death, the maximum entropy state, has a very specific geometric property. It's conformally simple. Conformal geometry is a mathematical framework that deals with angle-preserving transformations, transformations that preserve the shape of things but not their scale. In a conformally flat space-time, the global structure of the geometry looks the same regardless of what scale you're examining. The distances between things don't matter in a conformally invariant description. Only the angles, the causal relationships, the light cone structure. Now here's what Penrose noticed. At the very end of the universe, in the far future, when everything massive has decayed or been swallowed by black holes that then evaporate, when all that remains are massless particles, photons and gravitons, traveling at the speed of light, the universe becomes conformally simple. Massless particles don't experience time. For a photon, there is no such thing as the passage of proper time photons travel at c, and the proper time along a null geodesic is 0. In a universe populated only by massless particles, proper time ceases to have physical meaning. And here's the remarkable thing. The very early universe, just after the Big Bang, in the first tiny fraction of a second, is also conformally simple for a different reason. In the hot, dense, radiation-dominated early universe, the physics was also essentially scale invariant. The thermal equilibrium of radiation is conformally invariant. The structure of quantum fields in the radiation-dominated epoch is, to a good approximation, conformally invariant. So we have two eons, the far future of one universe and the early moments of another, that are both conformally simple. And conformal simplicity means that the geometric boundary conditions at these two eons can, in principle, be matched. The end of one universe and the beginning of another can be sewn together in a way that's geometrically consistent. This is the central insight of conformal cyclic cosmology. Penrose is not saying that the end of the universe loops back to its own beginning. That's not the topology he's describing. He's saying that the end state of one universe, what he calls an aeon, can serve as the Big Bang of the next aeon. The conformally flat geometry of the dying universe matches, after a conformal rescaling, the conformally flat geometry of the nascent universe. The boundary between them, the crossover, is a smooth geometric transition, not a singularity. The universe is not eternal, and it doesn't loop, but it does have predecessors and successors, an infinite sequence of aeons, each born from the conformally rescaled end of the previous one, extending infinitely into the past and infinitely into the future. Now let me explain what conformal rescaling means, because I think it's the key to understanding why Penrose thinks this can work, and it requires thinking about the role of mass in physics in a way that's subtle and important. Massless particles, photons, gravitons are blind to conformal rescaling. They don't have a rest frame, they don't experience proper time, and the angles they travel at the causal structure they trace are preserved under conformal transformations. If you scale up the metric, stretch the geometry uniformly, massless particles don't notice. Their paths, their interactions, their behavior are all conformally invariant. Massive particles, electrons, protons, atoms, are not conformally invariant. They have rest mass, they experience proper time, and their behavior is sensitive to the scale of the metric. They notice when you stretch the geometry. Now consider the far future of the universe. Everything massive has decayed. The proton lifetime, while extraordinarily long, greater than 1034 years, is finite in most particle physics models. Eventually, even protons decay. Black holes evaporate. Everything that has mass eventually either falls into a black hole or decays into radiation. What's left is a universe of massless particles. In this massless universe, conformal invariance becomes exact, not approximate. And a conformally invariant universe has no preferred scale. There's no way to define what big or small means, because massless particles don't carry scale information. In the absence of mass, the concept of distance becomes meaningless. The universe can be conformally rescaled to any size, including, in the limit, a size comparable to the Planck scale. Penrose's insight is that this conformally invariant future of our universe, this massless, scaleless endpoint can be geometrically matched to the conformally invariant beginning of the next aeon. The Big Bang of the next universe is not a singularity that appears from nowhere. It's the conformally rescaled crossover from the previous aeon. And crucially, this is where the observational predictions come in. Things that happened in the previous aeon leave marks on the crossover surface. Marks that are then inherited by the next aeon. Marks that might be observable today in the CMB, in the temperature fluctuations of the relic radiation from our own Big Bang. What kinds of marks? This is where the predictions of CCC become specific and testable, and where the observational story gets genuinely interesting. The most dramatic events in the late universe of the previous aeon are the final evaporations of supermassive black holes. These black holes, the remnants of galactic nuclei, accumulated over billions of years, are the last massive objects to persist in the dying universe. They evaporate through Hawking radiation over timescales of 1067 years for stellar mass black holes and 1093 years or more for supermassive ones. As they evaporate, they emit Hawking radiation, thermal radiation, with a specific temperature inversely proportional to the black hole's mass. The final evaporation of a massive black hole, when the black hole has lost most of its mass and is in its final moments, is an event that produces a burst of energy. Not a gentle fade, but a dramatic final explosion as the temperature of the Hawking radiation rises toward infinity in the last instance. This burst of energy, released in a universe that is otherwise settled into equilibrium, propagates outward through the dying universe as a spherical wave. It's a disturbance in the geometry, a pulse of radiation that expands outward from the black hole's final location. Now, remember that this dying universe is conformally matched to the beginning of our universe. The geometry is continuous across the crossover. The spherical burst from the previous aeon's black hole evaporation is mapped through the conformal rescaling onto a circular feature in the temperature distribution of our universe's relic radiation, the CMB. A circle, a ring, a specific geometrically defined circular pattern in the CMB temperature fluctuations corresponding to the location and scale of a supermassive black hole's final evaporation in the previous aeon. This is a specific, quantitative, falsifiable prediction. CCC predicts that the CMB should contain anomalous concentric circles, rings of slightly different temperature than the surrounding background. Not a single ring from a single black hole, but potentially many rings from the many supermassive black holes that evaporated in the previous aeon. And these rings have a specific statistical signature. They're more regular, more concentrated, more precisely circular than what you'd expect from the random fluctuations that standard inflation predicts. Have these rings been found? This is where the story becomes complicated, and where I want to be especially careful to represent the science accurately, because the history of the observational search for CCC's predicted circles is a story of claims, counterclaims, reanalyses, and ongoing debate. Not a clean story of discovery and confirmation. A real scientific debate with legitimate disagreements about statistical methodology and the interpretation of data. In 2010, Penrose and his collaborator Vahe Gurzadyan published a paper claiming to have found evidence for concentric circles in the WMAP CMB data rings of anomalously low variance in the CMB temperature fluctuations at specific angular scales, with a statistical significance that they argued was inconsistent with standard inflationary predictions. The paper generated enormous attention, and it generated immediate, vigorous scientific pushback. 3 separate groups working independently reanalyzed the same WMAP data using different statistical methods and found that the circles Penrose and Gurzadyan identified were not statistically anomalous, The circles existed in the data, but circles of similar significance appeared with comparable frequency in simulated CMB maps generated by standard inflationary models. The rings were not unique to CCC's predictions. They were consistent with what random fluctuations would produce. Penrose and his collaborators disputed this conclusion. They argued that the other groups had used incorrect simulations, that their simulated skies didn't properly account for the specific statistical properties that CCC predicts. The debate became technical, turning on questions of exactly what statistical test to use, what null hypothesis to compare against, and how to properly account for the look elsewhere effect, the statistical penalty you pay when you search for patterns in a large data set and then assess the significance of what you find. The debate has continued through subsequent analyses of the Planck CMB data, which is more precise than WMAP, with some papers claiming to find the predicted circles at marginal statistical significance, others claiming to find no evidence beyond what random fluctuations would produce. This is the honest state of the evidence, not confirmed, not ruled out. A contested marginal signal in a noisy data set with ongoing disagreement about the correct statistical framework for assessing it. But here's what I find genuinely interesting about the CCC debate and why I think it's worth discussing, even in its currently unresolved state. The disagreement is not primarily about the data, it's about what model to compare the data against. When Penrose's group says the circles are anomalous, they mean anomalous relative to standard inflationary predictions. When the critics say the circles are not anomalous, they mean the circles appear in random realizations of the inflationary model at a rate consistent with the observed frequency. Both statements can be simultaneously true if there's something wrong with the inflationary simulations used for comparison. And here's what makes this interesting. There are known anomalies in the CMB features that are statistically unexpected within the simplest inflationary models that have been confirmed by multiple independent analyses. These anomalies include the quadrupole suppression, the fact that the largest scale temperature fluctuations in the CMB are anomalously small compared to the predictions of the simplest inflationary models. They include the cold spot, an anomalously cold region in the southern sky, substantially colder than any feature predicted by standard inflation, whose statistical significance has been estimated at between 2 and 4 sigma. They include the hemispherical power asymmetry, a tendency for the CMB fluctuations to be slightly stronger on one side of the sky than the other. These anomalies are real. They've been confirmed in the Planck data, which is the most precise CMB measurement ever made. Whether they're produced by cosmic variance, the random statistical variation inherent in observing a single realization of an inflationary universe, or whether they represent genuine departures from the standard model is actively debated. CCC is one of several theoretical frameworks that attempts to explain these anomalies to provide a physical mechanism that would naturally produce the large-scale features that inflation doesn't predict. Whether CCC's specific predictions are the right explanation is unknown, but the anomalies themselves are data that any complete cosmological model needs to account for. Let me now tell you about a second type of observational signature that CCC predicts, one that's distinct from the circles and that provides a partially independent test of the theory. It's called the Hawking points. When a supermassive black hole evaporates in the previous aeon, not in the final catastrophic burst, but in the extended Hawking radiation emission over the long evaporation, it generates a sustained stream of radiation that propagates outward through the dying universe. In CCC, this stream of radiation is mapped through the conformal crossover onto a specific feature in our universe's CMB. The feature is a localized hotspot, a point source of elevated temperature in the CMB corresponding to the location of the previous aeon's evaporating black hole. The hotspot should be surrounded by a ring of lower temperature, a specific ring structure created by the geometry of the Hawking radiation wave pattern. These Hawking points should be detectable as anomalous temperature features in the CMB points that are significantly hotter than their surroundings, with a specific radial temperature profile that differs from the random fluctuations that standard inflation predicts. In 2018, Penrose and collaborators published a paper claiming to find evidence for Hawking points in the Planck CMB data. They reported finding an excess of hotspots with specific temperature profiles, more hotspots of the specific type that Hawking radiation would produce than expected from the standard model, at a statistical significance of about 3 sigma. 3 sigma is the level physicists describe as evidence rather than discovery. It's significant enough to take seriously, but not significant enough to conclude the effect is real. It means the probability of seeing the claimed excess by chance, if the standard model is correct, is about 1 in 1,000. Again, this claim has been disputed. Other researchers have argued that the statistical analysis used different trial statistics than those pre-specified, that the comparison simulations don't fully represent the standard model, and that the apparent excess disappears when different, arguably more appropriate statistical methods are applied. The Hawking points, like the concentric circles, are a claimed signal that hasn't been confirmed to the standard of scientific consensus, but also hasn't been definitively refuted. The debate continues. Now, I want to step back from the specific observational claims and address something about the theoretical framework that I think is important for understanding what CCC is actually saying about the universe. One of the most striking aspects of CCC is what it implies about information. We've discussed information preservation in the context of black holes, the question of whether information is destroyed when a black hole evaporates. CCC takes a specific position on this question. In CCC, information is not perfectly preserved through the conformal crossover. When the dying universe is conformally rescaled and matched to the beginning of the next aeon, specific information is transmitted the locations and energies of the black hole evaporation events, which are encoded in the circles and Hawking points. But the detailed quantum state of the previous aeon is not transmitted. The entropy is reset, or more precisely, the conformal rescaling effectively wipes the slate, producing a new universe that begins with a low entropy, conformally smooth state. This is actually one of the most attractive features of CCC from a theoretical standpoint. The low entropy beginning of our universe, which we discussed in our last conversation about eternal inflation and the Big Bang, is not explained by inflation alone. Inflation can smooth out spatial irregularities, solving the flatness and horizon problems, but inflation doesn't explain why the universe began in a low entropy state in the first place. The low initial entropy has to be put in by hand. It's an assumption of the model, not a derived consequence. CCC offers a partial explanation. The conformal crossover effectively resets the entropy because the conformally invariant end state of the previous aeon, the massless, scaleless, structureless, asymptotic future, is geometrically smooth. The next aeon inherits this smoothness as its initial condition. The low entropy of the next aeon's beginning is a consequence of the conformal geometry of the previous aeon's end. This is not a complete explanation. It shifts the question back to why the very first aeon had low entropy, but it does provide a mechanism for entropy resetting that happens naturally within the framework without requiring special initial conditions to be separately specified. I want to now address something that might be forming in your mind as a natural objection to the entire CCC framework. An objection that I think is important to engage with honestly. The objection is, even if CCC is mathematically consistent, even if the conformal crossover is geometrically possible, why should we believe that this is what actually happens. What physical mechanism drives the transition? What actually causes one aeon to give birth to the next? This is a genuine gap in the current development of CCC. Penrose has described the mathematical structure of the conformal crossover, how the geometry of the dying universe can be matched to the geometry of the nascent universe. But the physical mechanism, the actual dynamical process that implements this matching is not fully specified. Penrose's response to this objection is, in part, that the mechanism might not require additional specification, that the conformal structure itself, together with the laws of physics as we know them, might be sufficient to uniquely determine the crossover, the conformal invariance of the massless future, combined with the conformal invariance of the radiation-dominated past, might automatically produce the matching without additional physics. But this is not fully demonstrated. It's a direction of ongoing research, an attempt to show that CCC is not an add-on to existing physics, but a consequence of it. Whether this program will succeed is genuinely unknown. What I find intellectually interesting about this is the parallel to other theoretical frameworks in physics where the physical mechanism behind a mathematical structure was initially unknown. Quantum mechanics was discovered empirically before it was derived from deeper principles. The renormalization group in quantum field theory was understood as a mathematical procedure before the physical interpretation, the running of coupling constants with energy scale, became clear. Sometimes the mathematics leads and the mechanism follows. CCC might be, in this category, a mathematical framework that's pointing at something physically real, even if the complete physical mechanism isn't yet understood. Or it might be an elegant mathematical construction that doesn't correspond to physical reality. The history of physics includes both. Let me now tell you about something that connects CCC to the broader landscape of cosmological theories that attempt to address the pre-Big Bang question, because CCC is not the only serious proposal. And understanding how it relates to the alternatives illuminates what's distinctive about it. In our last conversation, we discussed eternal inflation, the framework in which our Big Bang was not the beginning, but a local event in an eternally inflating background, with our universe being one bubble among infinitely many. Eternal inflation and CCC are both attempts to address the same fundamental question. What was there before the Big Bang? They give very different answers. Eternal inflation says an inflating background with quantum fluctuations generating bubble nucleations. CCC says a previous aeon with its own galactic history and its own supermassive black holes that eventually evaporated. One key difference is in what they predict should be observable in the CMB. Eternal inflation predicts, as I described in the previous conversation, potential bubble collision signatures, specific circular anomalies from collisions between neighboring bubbles. CCC predicts concentric circles and Hawking points from the evaporation events of the previous aeon's black holes. Both sets of predictions are being searched for in the Planck data. Both are claimed to have marginal evidence by their proponents. Both are disputed by critics. Another key difference is in the structure of what came before. Eternal inflation posits an infinite background that always existed with the BGV theorem, requiring that even eternal inflation had a beginning at some finite past time. CCC posits a cyclical structure with no absolute beginning. Each aeon comes from the previous one, extending infinitely into the past. There's also the question of what happens to the laws of physics across the crossover. In eternal inflation, different bubble universes can have different physical constants, the string theory landscape of possible vacua. In CCC, Penrose assumes that the same physical laws operate in every aeon. The conformal crossover is a geometric transition within the same physics, not a transition between different physical frameworks. Whether this assumption is justified, whether the laws of physics are the same in every aeon, is itself a deep question. If the fundamental constants can vary, the concentric circles and Hawking points from the previous aeon might have different energies and positions than CCC predicts in our universe. Testing this assumption requires either finding the predicted signals and checking that they match CCC's specific quantitative predictions, or finding no signals at all. Now I want to take you somewhere deeper, into what I find most philosophically profound about conformal cyclic cosmology and about the broader question of what came before the Big Bang. Both eternal inflation and CCC share a common structure. They both say that our Big Bang was not the beginning, that there was something before it, but they differ in what kind of something that was. Eternal inflation says the same kind of physics we have now, just in a different geometric phase, exponentially inflating rather than expanding at a decelerating rate. The pre-Big Bang state is continuous with our own physics. It's described by the same quantum field theory and general relativity that govern everything we can observe. CCC says something more radical. It says that the pre-Big Bang state was a different aeon, a universe with its own cosmological history, its own galaxies and stars and black holes, unimaginably remote from us in time, connected to us only through the thin thread of conformal geometry at the crossover. The previous aeon was not just a different phase of physics, it was a whole history stretching over an even vaster expanse of time than our own aeon will last. The previous aeon contained, if CCC is correct, everything our universe contains: galaxies, stars, possibly planets, possibly life. It had a beginning of its own, the conformal crossover from the aeon before it. It evolved over a period of time that makes our universe's 13.8 billion years look like an eye blink. The evaporation of the final supermassive black holes takes 1093 years or more. And then it ended not in catastrophe, but in a long, patient fade to a conformally smooth geometry that became the Big Bang of the next aeon. If this picture is right, and I want to emphasize again that it's a theoretical hypothesis, not established fact, then the universe we inhabit is not the first universe. It's one episode in an infinite series of cosmic histories, each one inheriting its initial conditions from the conformally rescaled end of the previous one, each one lasting for unimaginably vast stretches of time, each one leaving its marks, circles, hot spots, the signatures of its most massive black holes on the CMB of the next. We're not the first, not in the sense that someone came before us and left ruins, but in the sense that the universe itself has been here before in other forms, in other configurations, with other histories, and our universe is the latest chapter in a story that may have no beginning. I want to close this first part with something that I think captures the essential character of what CCC and the search for pre-Big Bang signatures represents in science. Most questions in science are questions about things we can, in principle, observe. How do stars evolve? What is dark matter? How did the solar system form? These are hard questions, but they're questions about physical processes happening in or accessible from our observable universe. The question of what came before the Big Bang is different in kind. It's a question about a state of the universe, or of whatever came before the universe, that is, in the standard picture, causally disconnected from our observable universe. There's no light from before the Big Bang that has reached us. There's no causal influence from the pre-Big Bang state that can affect us now, or so we thought. CCC changes this. It says there is a causal connection that the previous aeon's physics is encoded in our CMB, that we can, in principle, read evidence of the universe before ours in the oldest light we can detect. that the pre-Big Bang question is not forever inaccessible to observation. It's already accessible if we know what to look for and how to distinguish the signal from the noise. Whether the signals are real, whether the circles and the Hawking points are genuine echoes of the previous aeon or statistical artifacts of analyzing finite, noisy data is a question being actively investigated. The resolution will come not from a single paper, but from accumulating evidence, improved CMB data, better statistical methods, and possibly from independent observational tests that CCC might suggest. In part 2, I want to go deeper into the physics, into what the conformal crossover actually involves at the level of quantum field theory, into what other theoretical frameworks, loop quantum cosmology, string gas cosmology, the ekpyrotic model, say about the pre-Big Bang state and how they compare to CCC, and into what the next generation of CMB observations from planned experiments like the Simons Observatory and CMB S4 might be able to tell us. Because the question of what came before the Big Bang, the question of whether we're not the first, is now, for the first time in the history of cosmology, a question that might have an observationally accessible answer. We're not the first, maybe. And finding out whether that's true is one of the most extraordinary scientific adventures of our time. So we'd arrived at this remarkable place where the question of what came before the Big Bang has moved from pure speculation into the domain of observational cosmology. Conformal cyclic cosmology predicts specific testable signatures in the CMB concentric circles and Hawking points from the physics of the previous aeon. The signals are claimed, contested, and unresolved. And the broader question, whether there was a universe before ours, is one that multiple theoretical frameworks are now addressing from different angles. Now I want to go deeper into the specific physics that makes the conformal crossover possible or impossible, into the competing theoretical frameworks that offer different answers to the pre-Big Bang question, and into what the mathematics of quantum field theory in curved spacetime, the specific technical physics that underlies these discussions, actually says about whether the universe can have a predecessor. But I want to start with something that I think is the most important conceptual point about CCC something that distinguishes it from other cyclic cosmologies and that reveals a specific tension with our current understanding of fundamental physics. The tension involves entropy. And specifically, it involves the second law of thermodynamics applied to the history of the entire universe. We've established that entropy always increases. The second law is one of the most fundamental and most experimentally confirmed laws in all of physics. Every process we observe, every physical, chemical, biological event moves from lower to higher entropy. The past is lower entropy than the future. The universe began in an extraordinarily low entropy state and has been evolving toward higher entropy ever since. In a cyclic cosmology, in any model where the universe goes through repeated cycles, you face an immediate problem. If entropy always increases, and if each cycle is a universe with its own entropy, then successive cycles should have progressively higher entropy. The first aeon starts with low entropy and ends with high entropy. The second aeon starts, if it inherits the entropy of the first, with high entropy and ends with even higher entropy. After many cycles, the entropy is astronomical. The cycles get larger and larger, more and more disordered. This is the entropy problem for cyclic cosmologies. And different cyclic models handle it differently. The ekpyrotic model, developed by Paul Steinhardt and Neil Turok, addresses this by having the entropy produced in one cycle diluted by an exponential expansion in the next cycle, so that the effective entropy per unit volume is reset even though the total entropy increases. This requires specific dynamics during the collisions between branes that drive the ekpyrotic cycle, loop quantum cosmology, which replaces the Big Bang singularity with a big bounce, where quantum gravitational effects halt the collapse of a previous universe and drive it into expansion phases, the same entropy problem. If the previous universe collapsed and its entropy was carried through the bounce, the entropy of our universe should reflect the entropy accumulated in all previous cycles. Conformal cyclic cosmology handles this differently, and this is one of its most elegant features and also one of its most debated aspects. In CCC, the entropy is reset at the conformal crossover, but not by diluting it or by some additional mechanism. The reset happens because the concept of entropy itself changes its meaning across the crossover. Here's the key insight. Entropy is a measure of the number of possible configurations of a system compatible with its macroscopic description. High entropy means many possible microscopic configurations. Low entropy means few. But, and this is the subtle point, what counts as a possible configuration depends on what physical processes are available. A gas at high temperature has many possible configurations because its molecules can move in many ways. A gas frozen into a crystal has fewer possible configurations. In the conformally invariant, massless far future of an aeon, the notion of configuration changes fundamentally. Without massive particles, without rest frames, without the concept of distance, many of what we would normally count as distinct configurations become identical. The entropy count properly done in the conformally